In last video, we talked about hexokinase and glucokinase in terms of Km value and Vmax value. Okay, so that topic is done. In part 2, you can watch that. So this video, we're gonna understand the why of why nature decided that. Why nature decided to give us. What's the evidence? Maybe it will be a little boring video for you because I think we'll have a lot of topics that already have been done, right? So the topic of today's video is why the liver waits while everyone eats, right? We'll understand fat state. What is fat state? We'll understand fasting. What is fasting, right? These are basic things. We'll understand diabetic ketoacidosis. We will understand the why of diabetic ketoacidosis. We'll understand glycogenesis, right? How the glycogen synthesis happens, right? We'll not go into the pathway exactly, but we'll understand how glycogenesis and pancreatic beta cells, how all of them are related in the question why liver waits, right? So we understood that. So now we already understand that glucokinase and hexokinase exist, right? We understand that Km value and Vmax values, right? And now we're gonna answer that why did evolution chose that glucokinase is going to stay in the liver instead of everywhere else, right? So let's understand this, right? So to understand this question, I want you to imagine situation number 1. So this is situation 1, right? So in here, you have not eaten for fasting. You have been fasting for 14 hours, right? Your blood glucose is around 70 milligram per deciliter. In situation 2, right, you just ate some carbs, maybe rice, right? Situation 2 is you just had rice, right? Your blood glucose is around 180, or maybe let's make it 160 milligram per deciliter again, right? Now the question here is this, that in both of the situation, should the liver behave same way in both situations, right? This is the question, and the answer is not. Now, of course, the liver will behave differently, but the question is, why not? That's the question. Now, everything depends upon whether you are fasting and fed, right? Everything depends upon if you're fasting or not fasting, all right? So let's understand the fed state first. So the fed state. So what is fed state, right? A lot of people will think, I just ate. That's fed state. Yeah, that's true. That is true, right? But fed state means food. Fed state literally means food is available. That's fed state right there. And this changes the priority of every organ, right? So when you just ate, when you're just in the fed state, what happens is that, let's start one by one, okay? What happens just after the meal, right? So we are understanding fed state. To understand fed state, we are gonna eat something, right? So let's follow the food. So food, right? Food goes in your mouth, goes through the digestion, right? So digestion happens, right? Starts in your small intestine. Now the glucose is absorbed, right? Glucose absorbed, right? Goes to the portal vein first. That's very important. Goes to the portal vein. Now the portal vein takes the glucose to the liver itself. Now from the liver, it goes to our systemic circulation, to all of the body, systemic flow, right? This is how the food moves when you just had a big meal, right? Now, I want you to note something, that liver is the first organ to receive that absorbed glucose. Now, if liver wanted, it can remove almost all the glucose, yes, but it doesn't, Why? Why doesn't the liver take everything? Why doesn't it? Because I want you to imagine a family. Parents buy this grocery, right? Now, should one child eat everything immediately or not? No, the food should be distributed fairly, right? That's the thing. So the same thing that liver behaves. So liver behaves exactly like that. Liver acts like body's distributive center. So liver is like body's distributive center. That's the thing, right? Liver acts like a buffer, as I can say, right? It's a buffer, right? Now, this word appears in like a lot of books, right? Liver acts as a buffer, What is a buffer, by the way? Buffer is something that prevents large changes, okay? It stops these large changes. For example, a pH buffer is something that prevents sudden changes in your body, like kidney and lungs. These are two buffers. Similarly, liver prevents these sudden changes in your glucose, right? And here, for example, you drink this 1 liter of Coca-Cola, right? And it's like super duper sugary. Now, without liver, your blood glucose will shoot up dramatically, but it doesn't happen like that. When you drink this Coca-Cola, your blood sugar doesn't shoot up like immediately. Some of that glucose is stored, and that blood glucose rises much less dramatically. And this less dramatic rise is actually because of the liver. The liver smooths this curve of blood sugar. That's why we call liver as a glucose buffer. Now, how exactly does it buffer, right? That's what we want to know. How does it do it, right? What enzyme starts the process? Everything starts with glucokinase, right? Everything starts with that. So the reaction is that glucose, right, goes through glucokinase, and then glucokinase traps this glucose and adds a phosphate at 6th position of the carbon. So G6P, right? Now the glucose is trapped inside the cells of liver. Now where this G6P can go, that's the question here. The big question is here. Where do you think this G6P is going to go? Now everything depends upon the situation. The first pathway, right? The first way where it can go, okay, let me just make it right that. It can go G6P, this trapped, the first way is glycolysis. We can break down this glucose and we can make ATP out of it, right? 4 ATP out of 1. Just let me write ATP simply, right? That's ATP right there. Second pathway that this G6P can take is something called as glycogenesis or glycogen synthesis, right? So glycogenesis. Genesis means synthesis. Genesis, genesis, yeah. And the third pathway that it can go to is called pentose phosphate pathway, right? Pentose phosphate pathway. In this pentose phosphate pathway, we're gonna create something called as NAD. Now, not NADH. We're gonna make NADPH, and once we have NADPH, we can make ribose sugar. This ribose sugar can be used for what? For DNA synthesis. Okay, that's also very important, right? DNA synthesis, right? Okay. So liver chooses it according to the body's need, right? Now, why glycogen, first of all? Why glycogen? Why here, right? Why glycogen? Why not just push all the G6P into glycolysis, right? Why glycogen? Because tomorrow we may be fasting. That's a body conditioning. Body stores these extra glucose as glycogen. Think of glycogen as like just glucose saving account, simply. What about this process itself, like glycogenesis, right? Well, let's break the part. Glyco means glucose, genesis means creation, therefore glycogenesis means making glycogen, right? Now, when does glycogenesis happens? Well, it happens just after you eat, right? Mainly after the meals. Why? Because insulin is super duper high. Now, you might ask me, why does insulin promote glycogenesis, Shashwat? Well, what message does actually insulin provide? Or what message does insulin send? Well, simply it's like food is abundant. So insulin says, if insulin is high, it means food is abundant. That's the message, abundant, right? Therefore, when insulin is high, the breakdown of glycogen stops, right? They stop making glucose. They store the nutrition. That's why insulin is a storage hormone, right? It's the storage hormone, I should say. Right. Now let's come back to the main topic, right? Now imagine you have a patient, right? Let's come back to this why liver weights question, right? Now imagine you have a patient, right? You have a patient with diabetic ketoacidosis, right? Now in this patient of DKA, that is diabetic ketoacidosis, what are we gonna see, right? We're gonna see, first of all, we're gonna see thirst. This patient is gonna be thirsty, right? So patient's gonna be urinating a lot. She's gonna be peeing a lot, urination. We're gonna see ketones. That's very important, right? So ketones. What are we gonna see? We're gonna see a pH, acidic pH, maybe 7.1, right? Now let's talk about one by one. Like, let's talk about thirst. We call it polydipsia. Polydipsia, right? Now what's really happening here is that glucose rises, right? Glucose goes up. What happens when glucose goes up? Kidney are like overwhelmed by the amount of this glucose, right? Kidney cannot reabsorb the glucose because glucose is like huge in size. So glucose stays in the urine, right? So urine osmolality shoots up. Now water follows this glucose. You're gonna be dehydrated, and then once you're dehydrated, you're gonna wanna drink water. Yeah, that's the explanation for polydipsia. What about urination? Well, same again. Glucose causes osmotic diuresis, and then water follows the glucose. What about ketones? Well, this is the main part of the question, right? Why is liver making ketones when we have hyperglycemia, right? Why is liver making these ketones, right? What even is ketone? First question is that, right? So why is the liver making ketones, right? Because sugar is low or glucose is low? No, actually, in diabetic ketoacidosis, the hyperglycemia is there, right? So blood sugar is extremely high. The problem is that cells cannot respond to the insulin, right? So liver interprets this thing as body is starving. So fat breakdown starts, and fatty acids, they enter inside the liver, and then keto bodies are produced. Now, why the pH is 7.1? Due to ketones. Ketones are acidic in nature. So that's why we have metabolic acidosis, right? Ketones body are just acetoacetate and this beta hydroxybutyrate, I think, and they are super duper acidic in nature, right? So that's why the blood becomes acidic. Now, what does the insulin fix? How would insulin fix this? Simply, we give the insulin, right? We give the insulin, and will the insulin fix the problem? Does the insulin simply lower the disease, lower the glucose? Well, actually, it does more. Insulin actually tells the liver, hey, stop acting like we are starving, right? When you have enough insulin, the lipolysis goes, when we have enough insulin, the insulin tells the liver like, hey, stop it. We are not striving. We are not starving. We are not hungry. We are in a fed state, right? So lipolysis decreases, ketogenesis decreases, glycolysis also increases, glycogenesis increases, glyconeogenesis decreases. Now notice that one hormone coordinates many pathways simultaneously, right? So if we give insulin, let me repeat it. So insulin, right? We give insulin. I'm giving insulin to the child or to the guy, right? So insulin. Once I give insulin, the lipolysis, it's a catabolic. So lipolysis gonna go down because it's a catabolic pathway. What's gonna happen to ketogenesis? Ketogenesis happens when you are in ketogenesis. When does ketogenesis happens? When you are in a starving phase, right? When you are in a fasting phase. So it's gonna go down too. What about glycolysis? Glycolysis happens when you just had a big meal, right? And when do you have a big meal? What happens to the insulin? When you eat, your insulin rises. So insulin is saying, oh, you just ate. So glycolysis will increase because body will think, oh, you had a big meal right now. So fed state. What about glycogenesis? Glycogenesis. What happened to this one? Well, it's gonna also increase because you just ate the big meal, and if you have enough glucose, you can actually just I don't know, just build that thing, right? What about gluconeogenesis? Building up new sources from a non-carb source. building new glucose from non-carb source. That is gluconeogenesis. Gluconeogenesis. What happens here? It's gonna go down, right? Because this happens, gluconeogenesis. This happens when you're starving, right? When do you want to make glucose from a non-carbs? Sorry, when do you want to make glucose, right? It's like new glucose, okay? Neo means new. So new glucose from a non-carb source. When does it happen? It happens when you are short on carbs, right? So this one insulin is actually responsible for all these things, right? So why does glucokinase increases all of that, right? Now we reach the question, right? The patient receives insulin, right? Why should glucokinase increase? Because liver switches from glucose production to glucose utilization, right? When we give insulin, right? Right? And what's going to happen? Liver's going to think, oh, we just had fed state. This person just ate. What's going to happen? Glucose production is going to go down because we already ate. The glucose is coming. It's on the way, This person just ate the food. So glucose production is going to go down to this phase where glucose utilization and storage, because the liver is thinking, wow, this person just had a big meal because we just gave him because we gave him insulin, right? Insulin is a message of fed state, right? So without glucokinase, the liver cannot efficiently trap the glucose, right? Now the question is, why would you, I'm thinking, why doesn't hexokinase increase, right? Hexokinase is found everywhere else, right? Hexokinase is found everywhere, but is not upregulated by insulin. Why? Because the brain, muscle, RBCs, they need glucose all the time, right? Not only after meals. Hexokinase is designed to function all the time, right? So its regulation comes mainly from the substrate availability, like glucose, right? And the product inhibition, like G6P, can just stop the hexokinase, not from insulin, right? What about pancreatic beta cells, right? We know that glucokinase, right, is present in the liver and beta cells, right? Why in beta cells? How does the beta cells know? How does the beta cell know when the blood sugar is going up? It cannot see the glucose directly. Instead, what happens is that glucose enters inside the beta cells. Glucokinase phosphorylate just like traps it, and glycolysis increases and ATP increases. And then what happens is that this increased ATP, right? This increased ATP closes the ATP sensitive potassium channels. We call this as KTP, KATP, right? KATP channels. And once these channels are closed, the cell membrane depolarizes it, right? Goes to a positive charge. Now, once it reaches that depolarization state, right? What happens is that these voltage gated channels, these calcium channels, they open up. Once these voltage channel open up, right, these calcium channel open up, the calcium influx increases. So calcium levels goes up. Once the calcium is, enough, the Golgi body sense that calcium, and then, they're like, okay, time to release insulin. So that's how your insulin is actually released, right? Now, this is super duper high yield mechanism, I think. And glucokinase is the acting as glucose sensor here. Okay, so glucokinase allows the glucose to be trapped or sensed, right? Sensor here, all right? So glucose enters the cells, glucokinase phosphorylates it, traps it. Now glycolysis starts, and then we have increased ATP, right? So we don't need oxygen, by the way, in insulin secretion, right? And then once the ATP is enough, it closes these channels called KATP, that is potassium ATP sensitive channels. They close, and then depolarization, and then this whole chain occurs, right? This is the answer why glucokinase glucokinase is present at pancreatic beta cells, right? This is the answer. Why? Because it acts as a sensor. Okay, that's how it is. Now let's talk about if this glucokinase fails. Now imagine this glucokinase is a shitty glucokinase, doesn't work, not working, or failing, I should say. That's a better word. It's not working. What if glucokinase doesn't work, right? In this case, we will have something called as MODY type 2, right? MODY type 2. So in this, what is MODY? MODY is maturity, M for maturity onset diabetes of the young due to glucokinase mutation. What happens is here is that the beta cells underestimate your blood sugar, insulin release is delayed, and then mild fasting is going to occur even when you are in a hyperglycemic state, right? So here you will have hyperglycemia, and you're going to have ketones or slash fasting, I should say, right? The body behaves as such that the glucose is not there, but actually glucose is there. Now let's break this system. What if the liver had only hexokinase? Let's change the parts. So even if the liver had only hexokinase, now even when the fasting is happening, the liver would continue to trap the glucose aggressively, and then the availability of glucose would just go down for the brain and for the RBCs. Less glucose available for the brain, so it's like poor survival for starvation. You will not survive in like fasting of 10 days or 5 days. You will just die. What if beta cell like glucokinase will have this MODY, right? Of course, blood glucose could rise, of course, but insulin secretion would be just bad, impaired, because beta cell would not sense the glucose, right? So the whole summary of this concept, this video, is that liver acts like a glucose buffer, protects the body from these large swings of potassium and glucose. That's very important. Potassium, right? You eat a bag of chips. You eat this bag of chips. Now, it has like insane amount of potassium, but you don't die of heart attack. Why? Because of liver. Liver makes this insulin and it stores this, gulp down this high, insane amount of potassium and glucose, right? So that's how it works. Why you don't die even after like eating this insane amount of potassium from salt, right? And from chips and these, I don't know, fast food, right? So liver acts like a glucose buffer, protects the body from these large swings of blood sugar. Insulin promotes the glucokinase, right? It increases phosphorylation of glucose after meal. Glucokinase is present in liver and pancreas, beta cells, right? Beta cells, these glucokinase functions as like glucose sensor here, right? And MODY type 2 is caused by mutation in glucokinase, right? Leads to hyperglycemia and fasting, right? So that's it. That's the concept in the liver. That's the concept. That's it. I don't think I need to speak more on this topic. Have a nice day.